Hello, today we'll be reviewing the F equals to MA 2025 problem 7. The problem states as follows. A mechanism consists of 3 point masses, each of mass m, connected by two massless rods of length L and a torsion spring acting as a hinge. The potential energy of the torsion spring is given as U sub S. This system is designed to walk down a set of stairs, as shown in the figure. The angles θ1 and θ2, see figure, represent the orientation of the rods, and their rates of change, ω1 and ω2, are the corresponding angular velocities. Assume the mass on the surface is instantaneously at rest. Which equation correctly describes the total energy of the system? Before we begin, let's outline a basic idea of how we are going to attempt this problem. One component of the problem is the torsion spring itself. The torsion spring in this case actually doesn't really play any role in finding the total energy of a system other than this US. So in this case, it can just be ignored. It doesn't really matter. So what we'll be doing is that when we get our total sum, we'll just add US to it. But what about these other two masses, these point masses M and N? Well, let's look at this first point mass. Let's label this system so that we can refer to it in a more organized fashion. Let this point be known as O, this point be known as A, and this point be known as B. I picked this point to be O because it is the only stationary reference in this entire diagram, and the stationary reference is typically denoted as O. What we will do is that let's first find the kinetic energy of A with respect to O. Then we will find the potential energy of A with respect to O. Then we will try to find the potential energy and kinetic energy with B with respect to O. This will be a bit of a more difficult process if we try to do it directly. So what we will do is that we will first find the kinetic and potential energies of B with respect to A, and then from there, just add that to kinetic energy and potential energy with A with respect to O, therefore giving us the total energy of the system. Let's dive into this problem and give it a shot. Okay, so now that you've seen the introduction to the problem, let's solve the actual problem. First of all, the potential energy of the spring is already given as US as shown here. So we already know this. Now let's look at the potential energy of A with respect to O. Because remember, we are going to be taking each of these objects with respect to another object that is stationary to make our computations easier. PE of A with respect to O is nothing going to be M times G times the height A has above O, and this would be equivalent to L sine θ1 by some basic trigonometry. Meanwhile, PE of B with respect to O would be equal to MGL sine θ1, as that would be this height, plus MGL sine θ2, which would be this height, giving us the total height above the ground. Meanwhile, let's find the kinetic energy of A with respect to O. This is equal to half times M times the absolute value, as when you're trying to find the kinetic energy of an object, the velocity will be expressed as a vector most of the time in physics. However, you need to take the magnitude of that vector or you'll be getting nonsensical results. So what we'll be doing is that we'll be taking the magnitude of the vector we get, and as the linear vector in this case would be nothing but the radial distance times the angular vector, which is ω1 times L. We'll be finding it in terms of that. The components will be ω1L cosine theta j, which is in this direction, and ω1L sine theta j, which is in this direction. Yes, I'm doing the system as shown here, such that x towards the right is positive and y down the downward direction is positive. I know it's unconventional, but in this case, that's what I'm doing. Meanwhile, KE with B with respect to O is going to be half times m with whatever the velocity of B with respect to O is. And the velocity of B with respect to O is going to be equal to velocity of B with respect to A plus velocity of A with respect to O. We already know the velocity of A with respect to O is from the previous notion. However, finding the velocity of B with respect to A is a pretty similar process, and in this case, it comes out to be omega 2L sine theta 2I plus omega 2L cosine theta 2J. Adding up the respective components from both parts of the vector gives us the total vector, of which we take the absolute value of to get this final kinetic energy as shown here. The total amount of energy just consists of the sum of these 5 components, which if you add them up, expand the expressions, and to show some trigonometric substitution, you will end up getting US plus 2mgl sine theta 1 plus mgl sine theta 2 plus m omega 1 squared L squared half omega 2 squared L squared plus m omega 1 m omega 2 L squared times cosine of theta 1 minus theta 2, hence giving us the solution to this problem. Pretty simple, huh? Alright, see ya.